Basically what expected value is when you take the first event, multiply it by its probability, add to that the second event, multiply by its probability, add to that the third event, multiply by its probability. You do all of those until you've accomplished all of the events. Now, for example, we had done this right here, right, which was where we flipped 3 coins, okay, and we were looking for heads coming up. 0 heads was a probability of 1/8, 1 head was a probability of 3/8, 2 heads is a probability of 3/8, and 3 heads is a probability of 1/8. Yes?
Could we have used the probability thing for the last chapter too, and have the same?
Well, yeah, sort of. It's the same principle.
I did it, and I'm pretty sure I got it.
Okay, well, cool. So let's go ahead and create the expected value for this. So I'm going to use the same exact chart. And we had 0, 1, 2, and 3. Exactly the same, right?
So if I got, like on the test, I got cut up, they know this is not a
Well, it might. I'm sorry. Okay. The 8 came from up here. We flipped 3 coins. What's the probability of heads showing? There's 4 possibilities. You flip 3 coins, you get no heads. Tail, tail, tail. You flip 3 coins, you get 1 head, which was, I don't know, yeah, tail, tail, head, tail, head, tail, head, tail, tail, head, tail, head. That. Flip 3 coins, there's a possibility of 2 and 3 heads showing, respectively. Those are the probabilities, okay? So, what's the expected value? Well, what I'm going to do is I'm going to look at this right here, and my expected value is going to first be the product of those 2 numbers plus the product of these 2 numbers plus the product of these 2. And finally, we're going to add the last pair of numbers, multiply together. And this is going to look like this. I'm going to have 0 over 8 plus 3 over 8 plus 6 over 8 plus 3 over 8. I don't recommend reducing any of the fractions until after you finally, or until you get your final sum. Do not reduce the fractions until you get your final sum, because this one right here will reduce down to 3/4, but then I've got to go ahead and find the common denominator again. If I leave it like that, I can just add the numerators, okay, and get 12/8. And then I will go ahead and reduce that and get 3/2, which is equal to 1.5. That's my expected value. Now, let's examine the expected value for a moment. Can I get 1.5 heads when I flip coins? No. The expected value is not necessarily going to be an event that actually occurs. Expected value is really useful when you're looking at large amounts of data and you are doing a probability distribution and you're trying to understand in this whole big grouping of numbers, what should I expect? Well, think about it. 1.5, there's 3 coins that we're flipping, and I get anywhere from 0 to 3 heads. So if I take 3 plus 2 plus 1, I get 6. If I divide that by 4, because there's 4 possibilities, that's 1.5. This is just another way of finding an average. Okay? That's all it is. It's just another way of finding an average. So let's look at checkpoint number 2. This one says find the expected value of the number of heads showing when 4 coins are tossed. Well, to do this, I want to go ahead and determine my probability distribution. That's the first step. So we're going to create the probability distribution.
And you can just do that 2 to the forward, right?
Right.
And it will be 60,
Okay.
right? So it will be 60 possibilities.
There is determine the possibilities for heads. Okay? Now, there's something called Pascal's triangle that will actually help us with this. Because if we go back up here and we look at this distribution, there are 0 heads showing. That's only one way that it could occur, right? 1 head showing, there's 3 ways that it could occur. 2 heads showing, there's 3 ways that could occur. 3 heads showing, that's one way that it could occur. Now, if I write these numbers down, I can also write something above it that looks like this. Now just bear with me, okay? This right here is going to be 2 to the 0 power, 2 to the first power, 2 to the second power, and 2 to the third power, where these numbers are the number of possibilities, right? You're the one that just came up with it, Jesse. What are you going to do for 4 coins? What did you say?
You're going to do 2 to the 4th.
Okay, so let's do that. We're going to do 2 to the 4th. This represents 4 coins, right? Now, if I add 1 and 3, what do I get? If I add 3 and 3, what do I get? If I add 3 and 1, what do I get? And then I'm going to bookend them with 1s, because that's the way Blaise Pascal determined a binomial distribution to work. Now, that right there represents my possibilities. So actually, let me take this right here and move it down.
So is this the possibility of heads?
Yep.
All of those is the possibility of heads. We don't have to do the tree diagram.
You don't have to do the tree diagram. The number of times you flip the coin. Okay? So the exponent is the number of times we flip the coin. Okay? Now, we create our chart. X and P of X, right? I've got 0, 1, 2, 3, and 4, because those are the possibilities, because I have 4 coins. So I'm either going to have no heads showing, 1 head showing, 2 heads showing, 3 heads showing, or 4 heads showing. Jesse already pointed out that 2 to the 4th equals 16 is the total number of combinations, or I should say total number of, I don't want to use the word combinations, total number of arrangements. So what's my denominator going to be for my probabilities? Okay, so that means we do 16 here, 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 and also there. And now I'm going to take and put 1 here, 4 here, 6 here, 4 here, and 1 here. Now, just for the sake of discussion, what do you think the numbers would be if I were flipping 5 coins and discussing the possibilities of heads occurring? There you go. See how cool that is? It is way cool. Or in the terms of us New Hampshireans, that's wicked cool. Wicked. Wicked is it's a timeless word. Wicked. It is. Everything's wicked. In New Hampshire, everything is wicked. All you got to do is watch an Adam Sandler movie. How many times does he say wicked? A lot. Yeah, he's also from my hometown, so I know he's Jewish. Manchester has a large Jewish population, which is our hometown. Yeah. Yeah, because a whole lot of Christians go around singing Hanukkah songs. Yeah. No. So is that a problem that he's Jewish?
No.
Okay, just checking, just checking.
Because I put it all together one day that every movie that he was in, there was some kind of Jewish tradition.
Yes, everyone.
Beat the Fockers. And is he in the movie? Yes.
No, he's not in that movie. That's Ben Stiller. Anyways, let's go back to something we know about, which is probability. Now, find the expected value. How do I do that? I'm going to multiply these two numbers together, right? And then I'm going to multiply these two numbers together. And then I'm going to multiply these. And then we'll have 3 times 4/16. And finally, we will add these. Okay? Now, that's going to be equal to 0 over 16 plus 4 over 16 plus 12 over 16 plus 12 over 16 plus 4 over 16. There we go. So add the numerators. 24 and 4 is 28. 32 over 16, right? And so what's my expected value actually equal to? 2. Yep. Okay. Now let's talk about where this really is useful. You sure? Do I need to go over it again? Four plus 12 is 16. 12 plus 4 is 16. 16 plus 16 is 32. Two times 6 is 12. Not 8. Oh, okay. Yeah, I don't do that. That's not right. Okay. So now does it make more sense? Okay, good. All right, now let's talk about where this stuff is really useful. Gambling. Yeah, it is. This is one of those things where casinos and any house that's running some sort of game determines the average winnings. Okay, basically that's what it is. Okay, and this is how you're going to determine how much you're actually going to lose. Okay, so we're going to look at this problem here. Let's say suppose you buy one of 10,000 tickets at $1 each in a lottery where the prize is $5,000. What are your expected net winnings? What does this answer mean? So let's talk about this for a moment. What do I actually have going on here? Well, there are 10,000 tickets, and they cost $1 each. Okay? So 10,000 tickets. Okay, so you've never gone to a fundraiser where they say, it's a raffle, buy a ticket for $1, you could win. It's the same thing. It's all the same thing. Yeah. Have you never played those? Yeah, why would you do that? Because of grand prizes on those things.
Well, but it said lottery, and I'm sitting here going,
Okay. When we say lottery, we're talking about any game of chance where you purchase a ticket and it's a raffle, basically. You know, we use that term here. I guess we use the term here in Alabama because for some reason it doesn't have a bad connotation. I don't know, but it's still the same thing. You're gambling, but that's legal. But I can't go buy, you know, a Mega Millions ticket, right? What's the difference? There isn't one. Yeah. Wouldn't that be nice? Wouldn't that be so cool? Anyways, I digress. So we have 10,000 tickets at $1 a piece. We also note that the prize is $5,000, which means that one of those tickets will yield that $5,000 prize. So one ticket yields a $5,000 payout. But what does that mean ultimately? It means that 9,999 tickets pay nothing.
Is it pay nothing, or is it one of those, like, you scratch and you get, like, $5?
No, it pays nothing. There's.
The only prize is that $5.
That's it. That's it. This is one prize. Boom. Now, we can do this for multiple prizes, and we did one in class on Thursday, didn't we? Yeah. So, now, what are your expected net winnings? Well, let's talk about this for a moment. What are net winnings? What does that mean? Net winnings. That's right. That's the amount that you win or the amount won, minus the cost of the ticket. So if you win $5,000, what are your net winnings? And let me fix this. Yeah. Yeah, let's just. So we take the 5,000 and we subtract the $1 that on a whim I paid for my ticket, which means my net winnings are $4,999. Now, what is your net winning if you win nothing? No. That's right, because I didn't win any money and I spent $1 and I am now in the hole, just like the federal government.
Hang on, so what if not all those tickets sell and nobody wins? Does that mean that you get more money? Is this with the assumption that all the tickets are going to be sold?
It's a good question, and I had wanted to save that for the end because that was one of the questions that I was going to posit to you guys. Okay? So hold your applause until after the presentation, and then we'll discuss it, okay? So, now, let's find the expected value, okay? Which means I'm looking at the event and the probability of the event occurring. So this right here represents one event, my net winnings of $4,999. And this right here represents the other event, which is a negative $1. So let's talk about the probabilities here. Let's see. Yeah, I'm sorry I'm drawing all these extra lines. I was told for the net winnings of 4,999. 1 out of 10,000. Excellent. This is 1 out of 10,000. Because there are 10,000 tickets up here. One ticket yields the $5,000 payout, which equates to the $4,999 net winnings. So, using the same logic, what's the probability for losing $1?
Or 9,999.
Exactly. Now, what's the expected value? The expected value, I take this pair of numbers and I multiply them together. I'm still going to use the color though, because I think it
helps most of us that.
and then I'm going to take this pair of numbers and okay, I got to put 10,000 comes from the fact that there are 10,000 tickets in this lottery or raffle, okay? Now, so you got to love this class because we talk about everything except for math. Okay, but, you know, so you guys have all finished my evaluations, right? Okay, good. You haven't?
You
I can't give you extra credit. I don't know if you've completed it or not. I know I can see how many have done it. Oh, so what you're saying is give you guys extra credit if everybody's done it.
Yeah, like 100% of yours. Wait, hey, she wants to She's like, where's the bill?
Okay. So we multiply these two fractions together. This one times this gives me this fraction. This one times that gives me that fraction. And I have 4,999 over 10,000 minus 9,999 over 10,000, which is going to give me a negative value. But we kind of expected that, right? What? It's not a probability, it's an expected value. Probabilities are always positive. However, expected values can be negative, and this basically reduces down to this. So what does that really mean? It means that on average, you will lose, lose 50 cents per ticket purchased.
Wait. So we bought the ticket. I'm looking at
I'm talking about overall, the entire experience.
Okay, so we bought the tickets, we sold the tickets, and we are also giving away a $5,000
Right.
prize. And after that $5,000 prize is given away, we have lost 50 cents?
No, you have.
Like, he bought the ticket.
I bought the ticket. You sold it to me. Yeah.
Okay, I'm the owner, he's the person.
I buy the ticket.
You buy the ticket. I give you
What
the ticket.
are my expected winnings? Negative 50 cents.
So
That's
you-
basically what it boils
so you
down to.
basically paid me 50 cents, and you lost.
No, I paid you $1 and roughly lost 50 cents because, and I'm not saying that's what I lost, but that's the expected value. And
Oh,
so if I bought 2 tickets, I lost $1.
you lost $1.
I lost $1. You gain money. And think about it, in this particular raffle here, what's the net profit, or what's the gross profit for the organizers of the raffle? $5,000. It's a great way to make money. As long as you sell all the tickets. Right. Okay? All right, we will call it a day.
Sounds good.